Welcome to Hononegah High School. I'm Brian Brown, and today we'll be looking at day 5 of our notes over chapter 3. And today we'll really be exploring more what's happening when we look at a number and we count how many significant digits we have. So while we talked about uncertain digit and so forth, now we're going to look at that a little bit more closely. And when we run around a number, so let's say we've got a number and we have to round it to just 3 significant digits, how do we do that? So this is really building on what we talked about yesterday. Now, before we get into that, I've got this little trick. So let's say the rounding rules aren't working for you and you're having trouble figuring out what's happening with a zero. This is just a little memory aid that I saw somewhere that it works every single time. And like any memory aid, there's no rhyme or reason to what it does. It just works. Now, really, you need to know in order to do this a little bit of geography. You need to know on the left side of the United States, we've got the Pacific Ocean, and on the right side, we have the Atlantic Ocean. So that's really critical. You have to know a little bit of geography here. If that doesn't make sense, then this really isn't going to work for you. But this is a trick that does work. So is the decimal point present, which would be Pacific? Remember, Pacific is left. So is the decimal point, and that's the P in Pacific, is present? I'll start on the left and count the first non-zero in every digit to the right. So if the decimal point is present, what we do is we start at the first significant digit on the left, and then we're going to count every non-zero and every digit to the right. So here is our first non-zero. So that's where we're going to start counting. There's 1, 2, 3. You've got 3 significant digits. Now, to me, honestly, it's a little easier to understand the rules. Rule 2 or 3 says zeros on the left, never count. Rule 3 says zeros on the right, count if there's a decimal. But it does really work. If the decimal is present, you start at the first non-zero on the left, and you go every digit after that to the right. Now, if the decimal is absent, then you're going to start on the right and you're going to count left. So start on the right side and you go to your first non-zero digit. So I'm starting over here. My first non-zero is a 4, and you count every digit to the left. Well, 3, 4, there's only 2 to the left, so that's only got 2 significant digits. So if it's present, you start at the first, go from the left and go to your first non-zero and count that in every digit after. If it's absent, start on the right and go to the left of your first non-zero and then count every digit to the left. Now, it's a bizarre thing. It happens to work every single time, and the Pacific is starting on the left and Atlantic is right. So it's a memory aid that works. I think it's just easier to know the rules though. Now, certain and uncertain digits. We talked about this yesterday, but I want to make sure, because in order to do what we're going to do next, which is math with this, it becomes very important that you're able to not just count significant digits, but understand where the certain and uncertain digits are. Now, when you're looking at a measurement, not only should we be able to count the correct number of sig figs, but it's also vital to some of the stuff we do mathematically to understand which digits were certain and which digit, not digits, but which digit was the uncertain digit. Remember, there's only one estimated or uncertain digit. Now, all of the certain digits, those are the known ones that everybody would agree what they are, plus that estimated digit are actually significant. So the uncertain digit then is always the last significant digit in the measurement. And this is what we looked at yesterday. So let's practice it again. So in this number from the set of numbers that we looked at, so we're going back to that exact spot in your notes. We said this first number had 5 significant digits. Well, what's our last significant digit then if they all count? Well, that's our last significant. So that has to be our uncertain digit. So what this says is underline the certain digits. Well, the 3, the 0, the 0, the 0, all those had to have been certain. And then circle the uncertain digit. Well, that's got to be that one. So that's a total of 5 significant digits. Next one had 4 significant digits. So that means this 3, this one, and this one all had to be our certain digits, and that one had to be our estimated digit for a total of 4 significant digits. Now this next one only had 1 significant digit. So this has to be my uncertain digit. There's only 1 digit there, so all I have is the uncertain digit. This is a very imprecise number. Literally what this would mean is 3,000 plus or minus 1,000. So our true value is somewhere between 2,000 and 4,000. So we have no certain digits here. All we have is the uncertain digit. Now the next one, we have a decimal, so those zeros count. So this one, and this one would be our certain digits, and that one would be our estimated digit for a total of 4 sig figs. Next one, 2 and the 3 are certain. That last 0 is my last significant digit. That's where my uncertain digit is. The next one, all those zeros count because there's a decimal shown, so that means the first 3 zeros and the 2 are all our certain digits, and our last significant digit would be the last 0. And then the final one, Remember, zeros at the beginning never count. So this is my first significant digit, and this is my second. And that would be my last, because zeros on the right count with a decimal. So that would be where my uncertain digit is. So when you look at a digit, you should be able to see which ones are just placeholders, which ones are certain digits, and where is the uncertain digit, the last significant digit. That's something you should be able to do with numbers if you really get them. And being able to do that, find the uncertain digit, that's really useful when we get into addition and subtraction next. Now, before we get to that, we're going to wrap up today with looking at when we round to a specific number of significant digits. So if we have some number and we want to round it to, let's say, 3 significant digits or 4 significant digits or 2 significant digits, how do we go about doing that? Well, I can't assume everybody remembers and knows exactly how you round, so I want to make sure we look at this idea. Now, first you're going to find the first significant digit in the number. Remember, that's the first non-zero, because at the beginning of a number, zeros never count. So find the first significant digit, and then you're going to start counting at that decimal place and count over the required number of places, and then underline that digit. So that's going to remind you, I want to round it here. So this needs to be the last significant digit that I write. Everything after that needs to be dropped because it's not significant. Now the underlined digit is the last significant digit, and everything else is going to be rounded out. So at that underlined digit, that's where we're doing the rounding. And remember the rounding rules. If the next digit, and so we're at the underlined thing, our last significant digit, and we look at the next number. If the digit is 5 or above, we round up. So 41.5 is going to be called 42. Now what we're really doing here is if we have a number like 41.5, and we're rounding at the ones place. So it's either 41 or it's 42. We're trying to decide which of these I should round to. And ideally what we want to do is the round to the one that it's closer to. So if it's closer to 42, we're going to round it to 42. If it's closer to 41, we're going to round it to 41. Now, 0.5 is exactly halfway in between the two. So how do we handle that? Well, in rounding, what they decided was, well, to keep things simple and everybody on the same page, if it's exactly halfway in between, the next digit's exactly a 5, then we're just going to round up to the 42. But that's why in math class they call it rounding up, is because we're either going up to 42 or we're going down to 41. We're doing one of those two things. And that's why we call it rounding up and rounding down. Now, if the next digit is 4 or lower, then we round down. So if I had 41.4 instead of a 5, 41.4, well, that's going to be closer to the 41 than the 42. So I should round down to 41. And that's really why your teacher calls it rounding down. I'm really leaving the decimal or the digit the same. I mean, 1 is still staying a 1, but I rounded out the 0.4, and think about what you did. You just made a number that was smaller than the one before. So that's really why we call it rounding up and rounding down. A better way to say it would be, if it's 5 or above, then round up. If it's 4 or below, then leave it alone. So literally you're just erasing the digits. But it is less, so that's why we call it rounding down. So if we had 41.51, well, that's more than 5. So it's 51. That's more than 50. So that's still the next digit is 5 or above. So my guess is we round up. If I had 41.49 here, well, my next digit is still a 4, and technically it's 49, but 50 would be half. We're at 49, so we're closer to 41 than we are to 42. So remember, you're looking at just the next digit. Anything past that is really irrelevant. We're only looking at the next digit past what you underline. So start at the beginning, go to your first non-zero, and count over. And then underline that digit. That's going to be where you round it at. So everything after that is going to disappear. So let's practice rounding a few of these. So first one, and if you're listening to this, what I want you to do is stop the tape and then go through and try and do it, and then turn the tape back on and listen to what the answers are. Okay, first non-zero is here, so I'm going to count over 1, 2, 3. So that's where I need to round. Well, my next digit is a 0, and since it's less than 5, that means I round down, and I get 3.00. So remember, I'm just rounding those out, and it's 3.0005 is a little bit bigger than 3.00. That's why you call it rounding down. Next one, same thing. Start at the first non-zero. That's right here. Count over 1, 2, 3. So now I'm rounding at the 5. Next digit's an 8, so I round 5 up to 6, and I get 9.06. Next one. This is a little bit trickier. I start here and I count over 1, 2, 3. So that needs to be my last significant digit. Well, my next digit is a 0, so they're going to round out. So that would give me 3. Oops, if I could write a 3, 3, 0, 0. And then the decimal is right here. I can't just get rid of those and change 30,005 into 300. So I still need my decimal to be over there. So I still need those zeros, but now they're placeholders. Well, how do I make this 0 count and that 0 count and that 3 count, but not have those count, the end zeros? Well, the only way to do that is scientific notation. So in this case, I've got 30,000 with 3 significant digits. It still has to be 30,000. But the only way to show 30,000 with only 3 significant digits is to write it in scientific notation. So 3.00 has 3 sig figs. And if I go 4 to the right with 3.00, I'm back to 30,000 again. So this is another one of those tricky ones where you had to put it in scientific notation. There's no other way to do it. Next, starting right there, count over 1, 2, 3. Now in this one, I want this 0 to count and none of these to count. So I've got 290. Next digit's a 3, so I round it down. But I want all 4 of those to not count, but that 0 to count. Well, I got the same problem as the last one. How do I make one 0 count but not the rest? Put it in scientific notation. And that would be 2.90 because I want that 0 to count. And then I had to go 1, 2, 3, 4, 5, 6. So times 10 to the 6th. So 2.90, 3 sig figs, times 10 to the 6th is still the same number, 2,900,000. Next one, 1, 2, 3. I'm rounding it to 0. Next digit's a 9, so I just round up to 1. So this one I didn't have to do anything goofy. This is one I could put in regular notation if I wanted to. I could show this number with only 3 sig figs, but there's no reason to change it because it doesn't say I have to put it in regular. Next one, and this is one that throws people when you first think about it, but realize if I've got 1, 2, 3, I've already got this rounded to 3 sig figs. So next digit, well, there is no next digit. So that already is the right answer. That is a number rounded to 3 sig figs. So just because the calculator gives you an answer doesn't mean you're always going to end up changing it. If the calculator shows 3 sig figs and you need 3 sig figs, that's just what you write. Next one, none of these zeros count. So zeros at the beginning don't count. So I start counting here. 1, 2, 3. Next digit's an 8, so the 0 rounds up to a 1, and I get 0.000451. Didn't need scientific notation. I could put it in it if I wanted to, but I don't have to have it in this case because I can show that with 3 sig figs. And then the last one. This is another one that's kind of tricky because you're not used to having to do this. Your calculator says 23. That's only got 2 sig figs. So how can I mean 23 but have 3 sig figs? Well, 23.0. That would give me 3 sig figs and it still means 23. So that's a 0 on the right. There's a decimal shown. It counts. So that's got to be how I would write 23 with 3 significant digits. I just add a 0.0. If I needed 4, I'd write 23.00. And remember, just as a quick review, the only way to show these two numbers here in the middle was to actually put them in scientific notation, and that sometimes happens. So remember, if you try and write it and it's just not working, you probably need to put it in scientific notation. Then you can have it show the correct number of significant digits and still keep it being the same number. Because we can't just change the number. 3,000 still needs to be 3,000. So we can't just write it as 30 decimal point because that would give us 2 significant digits in a quick, easy way. We've changed the number. So we have to put it in scientific notation. And 3,000 with 2 significant digits, we'd put 3.0 times 10 to the third. And that means 3,000 still, but it shows 2 sig figs. And that ends our day of notes over sig figs.